Hi everyone, we are from Group 4 and we would like to present our BEP proposal. So firstly, let me briefly introduce what is a ventilator. A ventilator is a medical device used to assist patients who have severe breathing difficulties. It helps to pump rich oxygenated air into the lungs and also helps to expel carbon dioxide from the human body. There are two types of mechanical ventilation, which are the non-invasive ventilation and invasive ventilation. Non-invasive ventilation involves the use of face masks, whereas the invasive ventilation involves endotracheal intubation. Invasive ventilation is preferred if the patient suffers from a more serious condition. Ventilator provides a lot of benefits to patients who have breathing issues because it allows patients to rest their respiratory muscles and provides patients time to recover until their breathing becomes normal again. Next, we proceed to the clinical issue. Water condensation in the ventilator tubing is one of the clinical issues that has been discovered during our visit to the NICU of the Department of Pediatrics in UMMC. Water condensation in the ventilator tubing is caused by the difference in ambient temperature and the pneumatic circuit temperature. Water condensation within the ventilator tubing presents a challenge to ventilator operation as it may obstruct airflow in the ventilator tubing and also triggers ventilator breath. It may also lead to ventilator-associated pneumonia as the contaminated condensate may drip into the patient's lung. In order to solve the issue of water condensation in ventilator tubing, 3 experiments are proposed. Next, we proceed to the hypothesis. The first experiment proposed is to study the effects of room temperature on inspiratory tube condensation. It is expected that as the room temperature increases, the inspiratory tube condensation will be reduced. For the second experiment, the effect of insulation of ventilator circuit tubing on temperature, relative humidity, and absolute humidity of the host in the ventilator tube circuit will be investigated. The assumption for this experiment is that the double insulation of ventilator tubing will maintain the temperature, relative humidity, and absolute humidity of the host in the ventilator tubing. The third experiment is to study the effects of the ventilator circuit tubing shape on the time taken for the occurrence of inspiratory circuit condensation. The assumed result is that the smooth interior ventilator circuit tubing will take a longer time for the condensation to occur as compared to the corrugated shaped tubing. Thus, by carrying out these 3 proposed experiments, the suitable design and features of the ventilator as well as the optimum ambient temperature for the operation of ventilator will be determined in order to solve the problems of water condensation within the ventilator tubing in ventilators.
Hi, I'm Yi Xun. For our first experiment, we plan to study the effects of room temperature on inspiratory tube condensation. So we are required to find out the relationship of surrounding temperature and the amount of condensation in respiratory tube. The ventilator functions to help patients with respiratory problems, and the rate of the air movement conducted can be adjusted by the therapist depending on the clinical needs. Usually, it is used together with heated humidifier to supply warm and humid air. However, the problem arises where condensation will occur inside the respiratory tube. The water droplets will be built up due to the temperature and humidity difference. Condensation problem must be minimized for effective ventilation and humidification. We predict that the outcome will be frequent condensation occur at the temperature range of 23 degrees Celsius to 25 degrees Celsius. Condensation can only be prevented by increasing the room temperature up to 27 degrees Celsius or even 28 degrees Celsius.
Hi, I'm Kang. I will present about the methodology of proposed experiment 1. The figure shows the equipment setup of the experiment. The name of each equipment is shown in the figure with number labeling. The blue line in the figure indicates breathing circuit, while the black line indicates power supply connection. Firstly, We need to carry out the experiment in a room with maintained humidity of 50% to 60%. Set the constant parameter of the ventilator. Positive and expiratory pressure, or known as PEEP, is set at 5 cm H2O. Ventilation rate is set at 10 times per minute with 1.5 second inspiration time, and oxygen concentration is set at 31%. Next, we need to select invasive mode for the humidifier. Set the room temperature at 23 degrees Celsius. Ventilate the simulated respiratory circuit for 12 hours. Make sure that the humidifier chamber outlet temperature is at 33 degrees Celsius and temperature at the Y-piece is 40 degrees Celsius during the experiment. Measure the weight of respiratory circuit before and after ventilation every 3 hours using digital infant scale. While measuring, the ventilating process is temporarily stopped. Calculate the amount of condensation by using the formula amount of condensation equal to weight after measurement minus weight before measurement. The step after that is we need to repeat thrice for each measurement and calculation to obtain the average value. Ventilation was initiated at each temperature after at least 1 hour had passed since the temperature reached the determined temperature. We need to repeat the measurement for different room temperatures at 25 degrees Celsius and 27 degrees Celsius. Lastly, we need to tabulate the amount of condensation after each calculation and plot the average condensation. That's all from me. Thank you.
So as what we expected, the outcome should show obvious decrease on amount of condensation in the breathing circuit from 23 degrees Celsius, 25 until to 27 degrees Celsius when the administration time becomes longer. Until 27 degrees Celsius, it may be no condensation occur. So this is how the graph will look like. That's all for the first experiment. Thank you.
Then I'll explain about experiment 2, which we are going to study the effect of insulation of ventilator circuit tubing on temperature, relative humidity, and absolute humidity of the host in this ventilator tube circuit. For ventilator, we notice that there's condensation occurs in the host. So condensation is the change of a substance from a gaseous into liquid form over the dew point, and the dew point is referred to the temperature at which the water vapor in the air condenses into liquid form. The hypothesis of this experiment is the higher the relative humidity of atmosphere, the closer the dew point to the temperature of air, and the greater chance of condensation occurs in the host. So there's high air temperature and high relative humidity of the air in the normal host, and causes the condensation occur at higher temperature in humid circumstances. So in this experiment, we are going to propose a hose cover to insulate the host to prevent condensation occurs. With greater thickness of hose cover, it keeps the host warm and prevent the formation of water droplets within the host. And with high quality soft elastic fabric material, it will dissipate the noise of the ventilator hose when the patient is sleeping on the bed, and also preventing the hose from damaging by covering the whole host of the ventilator. Other materials and equipment of this experiment. First, we are going to have a Hamilton H900 humidifier with hose, a fleece fabric hose cover, an anemometer DT892, and an electronic thermometer. So first, we are going to heat this air humidifier and examine whether the humidifier was in an open control circuit, and the rotate switch for the humidifier was set to level 3 for temperature and humidification. Then, the measuring probe of an anemometer was inserted into the end of the hose to measure the airflow and ensure the airflow of the ventilator was constant. Next, the temperature and the relative humidity of outflowing air from ventilator tubing was measured at room temperature of 16.4 degrees Celsius and 23 degrees Celsius using an electronic thermometer. The mean values were calculated for the following 2 minutes once a steady state of the surrounding temperature was reached. Next, the absolute humidity was then calculated using Schumeller's formula, which the absolute humidity equal to the relative humidity multiplied with the 0.0387 multiplied T2 minus 0.6066 multiplies T plus 13.766. Then, the steps 2 to 5 were repeated with the hose with a hose cover, and the results were then calculated and tabulated in the table in the next slide. So at the end of the experiment, these are the expected outcome. First, we compare the temperature, relative humidity, and absolute humidity of the air at the end of the hose without insulation at room temperature 16.4 degrees Celsius and 23 degrees Celsius. So we notice that the higher the room temperature, the lower the relative humidity, and the higher absolute humidity of the air at the end of the hose. Next, we compare the temperature, relative humidity, and absolute humidity at the air directly at the humidifier and the air of the end of the hose. So we notice the temperature at the air directly at the humidifier was greater temperature, lower relative humidity, and higher absolute humidity compared to the air at the end of the hose. Finally, we compare these parameters again with a hose without insulation and with insulation, and the results was crafted at the graph below. And from this graph, we can see that the hose with insulation maintains the temperature, relative humidity and absolute humidity of the air by preventing condensation occurs from contacting the cool air outside the hose and the warm air inside the hose.
Now I'm going to discuss on experiment 3. The title of experiment 3 is to study the effect of ventilator circuit tubing shapes on the time taken for the occurrence of the inspiratory circuit condensations. Our question is that does the standard corrugated design of the ventilator circuit tubing contributes for the occurrence of the inspiratory circuit condensation? So now here comes with the hypothesis. The standard corrugated design of the ventilator tubings leads to a larger total surface area for the heat loss and creates air turbulence, thus taking a shorter time for the condensations to occur. Hence, we postulate that the smooth interior design will minimize air turbulence, reduce the total surface area for the heat loss, thus taking a longer time for the condensations to occur. For the methodology part, we have medical air socket, medical air hose, Cellcraft P series humidifier, corrugated design tubing, smooth interior design tubing, cellphone tape, ruler, scissors, and clock timer to set up this experiment. The medical air is input into the humidifier from the medical air socket through the medical air hose. Then the humidity level is set to 95%, the temperature at 35 degrees Celsius, and flow rate at 8 standard liters per minute to stimulate the real-life exhale air conditions of a normal, healthy adult. Then the EVA corrugated ventilator circuit tubing length is measured and fixed at 1 meter using a ruler and scissors. One end of the EVA corrugated ventilator circuit tubing is connected to the air outlet point from the Cellcraft E-series humidifier, while the another end is left free without any connection. The tubing is placed and fixed at C-shape on the table using cellophane tape to stimulate the real-life twisting conditions of the tubing. Then the power supply is on and the clock timer starts simultaneously to record the time taken for the occurrence of the inspiratory circuit condensations in the tubing. The condition of the tubing is observed continuously until a positive condensation water droplet is noticed. Then the clock timer is stopped and the result is recorded. Lastly, the corrugated ventilator tubing is replaced with the smooth interior EVA tubing and the experiment is repeated again. Looking into the table on the left, the expected outcome of this experiment is the corrugated shaped ventilator circuit tubing has a larger total surface area for the heat loss, thus leading to a shorter time taken for the occurrence of the inspiratory circuit condensation. On the other hand, a smooth interior ventilator circuit tubing has a smaller total surface area for the heat loss, thus taking a longer time for the air condensation process to occur. Hence, you can see on the bar charts, which is on the right, shows the smooth interior tubing takes longer times for the condensations to occur. The smooth interior design ventilator circuit tubing will be better than the standard corrugated design.